In this video, we will be discussing the colligative property known as osmosis and the related osmotic pressure. Osmosis is the flow of solvent from a solution of low concentration into a solution of high concentration through a selective or semi-permeable membrane. A semi-permeable membrane allows solvent, but not the solute, to flow through it. The osmotic pressure is the pressure that must be exerted on the high concentration side to stop the flow. So looking at our diagram down here, we would have initially a side, two solutions, a low concentration and a high concentration that are separated by a semi-permeable membrane. What the semi-permeable membrane does is it allows the solvent molecules, in this case water, to flow from one side to the other. As soon as we mix solute particles into one side, making the left-hand side higher concentration, what you will find is that there is a net flow of the solvent molecules to the left-hand side. What this does is it decreases the volume on the right, increases the volume on the left, and you get a difference in height between the side that has a higher concentration compared to the side that has a lower concentration. Now we can stop the net flow of solvent molecules from the low concentration to the high concentration side by exerting a pressure on the top of the surface of the high concentration side. The amount of pressure that is needed to be pushed down on that high concentration side to prevent the net flow of solvent molecules between the left and right hand side is the osmotic pressure. Molecules will still flow back and forth between the different sides of the semi-permeable membrane, but the net flow will be zero. That means that for every one molecule that flows left, one molecule will flow to the right. That is if you are exerting the osmotic pressure value of pressure onto the side that has the higher concentration. Let's now work through a problem in which we determine that osmotic pressure. So a compound is found to have a molar mass of 598 grams per mole. If 35.8 milligrams of the compound is dissolved in enough water to make 175 milliliters of solution at 25 degrees Celsius, what is the osmotic pressure of the resulting solution? The equation for determining osmotic pressure is pi, we use that for our osmotic pressure, is equal to the molarity times our ideal gas constant, R, times temperature. The temperature here needs to be in Kelvin in order for the unit cancellation to work out. To solve this, what we need to do is figure out what our concentration of our solution is. So our concentration of our substance, we'll call it X, is equal, we take 35.8 milligrams. We need to convert this into grams in order to use our molar mass. 1 gram is 1,000 milligrams. Our milligrams cancel out. Multiply this by our molecular weight with grams on bottom, moles on top. 1 mole is 598 grams. Our grams cancel out, giving us moles. Now what we can do to find our molarity, we need to divide by volume. 1 over 175 milliliters, convert that into liters. 1,000 milliliters is 1 liter. Milliliters cancel out. The units that we're left with are moles per liter. If you plug this into your calculator, you'll get 3.4209 times 10 to the negative 4th molar. To figure out our significant figures, we go through our equation. Our first value has 3 sig figs. The next value is a definition, so it doesn't come into play. Our molecular weight has 3 sig figs. Our volume has 3 sig figs. And our last value is a definition. So that means that our resulting answer will have 3 significant figures. We can now plug this in to our equation and get the osmotic pressure, pi, is equal to our concentration, 3.4209 times 10 to the negative 4 moles per liter, times 0.08314 liter bar per mole Kelvin. Our liters cancel out, our moles cancel out, and we're left with bar per Kelvin. We can now multiply this by our temperature, 25 degrees Celsius. We need to convert that into Kelvin, which gives us 298. So we multiply this by 298 Kelvin. Our Kelvin cancel out, and we're now left with bar, which is a form of pressure. We can now bring this into the base unit of Pascal by multiplying 10 to the 5th Pascal is equal to 1 bar. That is the definition. Bar cancel out, giving us Pascal. If you plug this into your calculator, what you'll find is that your osmotic pressure is equal to 847.559 Pascal. In terms of significant figures, our first value had 3, our R value has 4, our temperature has 3, so our end answer will have 3 significant figures. So this comes out to be 848 Pascal. Osmosis and osmotic pressure have important real-world applications, particularly for those in the medical and biological fields. Cell membranes, which themselves are a form of semi-permeable membrane, allow the flow of water and small nutrient molecules between the outside and inside of the cell. By concentrating those nutrients inside the cell, you now have solute those nutrients, which creates an osmotic pressure in the cell. This keeps the cell swollen. Blood transfusions and IV feeding must have the same concentrations as blood. Solutions that have the same concentration as blood are known as isotonic. If the concentration is too low, this is what we call hypotonic. This will lead to cells rupturing because the concentration of the solute outside the cell membrane is too low, which will cause the solvent, the water in your blood, to flow into the cells, increasing the pressure to the point where the cell ruptures. If you have a situation where the concentration outside the cell is too high, so a saline solution that is greater than the isotonic concentration, we call this hypertonic. If the concentration outside the cell is higher, then via osmosis, the water will flow from the low concentration to the high concentration. This will cause the cells to shrink and die. Another important application of osmosis and osmotic pressure is the molecular weight of macromolecules, large biologics, can be determined by analyzing the osmotic pressure, as we will see in the following problem. Looking at problem number 2. A 150.0 milliliter sample of an aqueous solution at 25 degrees Celsius contains 15.2 milligrams of an unknown non-electrolyte compound. If the solution has an osmotic pressure of 8.44 torr, what is the molar mass of the unknown compound? So starting out, let's look at our equation for osmotic pressure. We have the osmotic pressure, pi, is equal to mRT. In this case, we have our osmotic pressure. We have R, because that's the gas constant. We have T is given in the problem. So here we're trying to find M. So let's rewrite this equation for M. M is equal to pi divided by RT. By knowing the concentration, we'll be able to figure out how many moles of this we have. We have the mass, and so we'll be able to determine our molecular weight. So M is equal to 8.44 torr times our R value. We're going to put the pressure on the bottom, so we get moles Kelvin on top. On the bottom, we'll use 0.08314 bar liter. Multiply this. Our pressure units don't quite cancel out right now, so we need to convert between the two so that they can cancel. We have 760 torr is 1.01325 bar. We can now cancel out our pressure units. Torr cancels out torr, bar cancels out bar. We want, in the end, moles per liter, so we need to get rid of the temperature. So we will divide by our temperature, or multiply by 1 over the temperature, which is the same thing as dividing. 298 Kelvin. Kelvin cancels out, giving us moles per liter. Plugging this into your calculator, you'll get 4.5417 times 10 to the negative 4th molar. So if we want to know the number of moles, for molecular weight we need grams per mole. So we can take our 4.5417 times 10 to the negative 4 moles over liters. In terms of significant figures for that value, our first one that was going in has 3 sig figs. Our R value had 4 sig figs. The value for our conversion between pressures is a definition. And then the last one had 3 sig figs. So our end answer will have 3 significant figures. Okay, to get moles, we need to take this value and multiply it by our volume. We have 150.0 milliliters, which we can convert to liters just by shifting the decimal place 3 to the left. So this would be 0.1500 liters. Liters cancel out, giving us Plug this into your calculator, you'll get 6.8126 times 10 to the negative 5th moles. Okay, now to find molecular weight, we just take our grams divided by our moles. So 15.2 milligrams, convert that into grams. 1 gram is 1,000 milligrams. Milligrams cancel out. And then we just need to divide this by our moles. So 1 over, sig figs there, 6.8126, mark our sig figs, times 10 to the negative 5th moles. Plug that into your calculator and you'll get 223.117 grams per mole. In terms of significant figures, this has 3, so our end answer would be the molecular weight of X, our unknown non-electrolyte, would be equal to 223 grams per mole.